Okay, so it's time to begin the class. Do you have any questions before we start? Okay, so if there are no questions, let's begin. So let's start by reviewing what we did so far. Yeah. So we started with some basic definition of rings and ideals, and we studied quotient rings. We saw isomorphism theorems, and after doing some basics of general ring theory, we came to some special kind of rings. The first in the list was Euclidean domain. So an integral domain is called a Euclidean domain if we have a norm which satisfies this property, which is related to the division algorithm. That is, if there exists AB in R, then for any AB in R, there exists Q and R such that A equals BQ plus R, with R either 0 or norm of R strictly less than norm of B. So that is a Euclidean domain. So it's basically an integral domain where you can carry out Euclidean, this division algorithm. And then we studied PID. So I think an integral domain is called a PID if every ideal is a principal ideal. And that is, every ideal is generated by one element somehow. Since I copied this from the other one, it only came half element generated by one element. Yeah. Then so we saw that every Euclidean domain is a PID. So in a Euclidean domain, every ideal is generated by one element. Then we define the notion of irreducible. So we a notion of an element being irreducible. So an element of the ring is said to be irreducible if it is a non-zero non-unit and you can't decompose it further. So you can't write it as product of two irreducible guys, two non-zero non-unit. Yeah. Any questions? There's some sound coming. Hello, is someone has a question? Maybe they have to raise the volume. No? Okay. Okay. Okay, so let's yeah, so an element is called irreducible if you can't write it as product of two non-zero non-unit elements. Yeah. And if it is said to be a prime if it satisfies this property that x divides AB implies x divides A or x divides B. Another way to think about irreducible is another definition of prime. So the only non-trivial factors of a prime are one and itself, right? So similarly, you can say an element is irreducible if its only factors are either unit or itself, more or less. Yeah. So something times a unit is also a factor. So we'll make that more precise today. Okay. And then we saw that every prime element is an irreducible element in any integral domain, and in a PID we saw that even the converse is true. So X is irreducible if and only if it is prime. So in PID, irreducible and prime are same, like integers. So PID is a natural integers is a good model for PID. So it's an example of a PID, and so is polynomial ring over a field. So we saw that. So in fact, we saw that Rx is a PID if and only if R is a field. So if R is a field, then Rx is a PID. We saw maybe a couple class ago, so so exactly a week ago, and then in the next class we saw the converse. And to prove that, we use this fact that in a PID, every non-zero prime ideal is maximal. Okay. So that's something very, and that gives you a good restriction, non-trivial restriction on PID. So any ring in which you can find a prime ideal which is not maximal, it's not going to be PID. So for instance, we saw that ZX, yeah, so we saw that ZX is not a PID because the prime ideal, the ideal generated by X or ideal generated by a prime number 2 is a prime ideal, but it's not maximal. And then we saw some non-trivial example. So we saw so these rings ZX, for instance, is not even a Euclidean domain. I mean, is not a PID, not a Euclidean domain thing. Yeah? So, but there is a distinction between PID and Euclidean domain as well. So anything which is not a PID is not going to be a Euclidean domain. But there are PIDs which are not Euclidean domain. So we sketched. So this is an example, and we sketched a proof of it. Yeah. So these adjoint 1 plus square root minus 19 over 2 is a PID, but not a Euclidean domain. So so I mentioned last time that this is an example of a ring of integers. Yeah. So so to show that, let me just recall what were the key steps. So the abstract notions at least we discussed, and computational part I just left it for you guys to check. Yeah. So the abstract part is that R is a PID if and only if it has a Dedekind-Hasse norm. So this Dedekind-Hasse norm is a weakening of the Euclidean norm. So it says that for all AB, either B divides A. So B, and that means A, if you write it as BQ plus R, so then R is 0. So either B divides A, or so compare it with the Euclidean norm. Yeah. So either B divides A, or and that is R is 0, or norm of AX plus BY is less than norm of B. Yeah. So it says that so it's slight weakening. So there we want in the Euclidean norm, Euclidean domain, we insist that X be 1, and we should be able to find Y such that A plus BY is has norm less than B. But here we allow A to be non-unit or not equal to 1. Yeah. So this characterization, we didn't see the complete proof. We saw the if part, but that is enough. So to conclude that this ring is PID. So if we show so the point is this this norm and the natural norm from this ring to Z, which we defined as an element times its conjugate, is a Dedekind-Hasse norm. So one can show that it's a Dedekind-Hasse norm, and that implies that the ring is a PID. So this characterization helps to decide decide that this ring Z plus square root of minus 19 over 2 is a PID. But it's not a Euclidean domain, and for that there was another result. R is a Euclidean domain, and so if R is a Euclidean domain and not a field, then it should have something called a universal side divisor. And what is a universal side divisor? So U is said to be a universal side divisor if for any element either U divides that element, or X minus U times Q is a unit. Okay. So U is a universal side divisor if given any element. Either if you apply this Euclidean algorithm to it, so either the remainder is 0 or the remainder is a unit. Okay, and then we showed that if something is a Euclidean domain but not a field, then it always admits a universal side divisor. But we also showed that this ring cannot have universal side divisor. Okay. So this is how one would conclude that this ring is a PID but not a Euclidean. So this is what this is where we ended last class. Yeah. Any questions? Okay. Okay, so if there are no questions, so today we will start the discussion on what is called a unique factorization domain. So unique factorization domain is a more general class of rings. So PID is an example, principal ideal domain is an example of a unique factorization domain. And this you get by axiomatizing a different aspect of integers. So we'll talk about it now. Yeah. So what is a unique factorization domain? Which is abbreviated as UFD. So a ring R, which is so an integral domain R is called a unique factorization domain. If every element in every non-zero non-unit element of R, you can write it as product of irreducible elements, and you can do that uniquely. Yeah. So essentially, uniquely, you can. So I'll say what uniqueness means in a bit, but what it says is that every element which is neither a unit nor zero, you can write it as product of irreducible guys. Okay, so in integers you can do that, right? Every integer you can write it as the prime factorization. Primes and irreducibles are same in integer, so there exists a prime factorization. And the small, I mean, in integers is unique in a stronger sense. Here it's unique because it's not unique in that strong sense, but it's unique in some up to a unit is what uniqueness comes out to, because our primes are slightly more general. So when we study primes in high school, we think of 2, 3, 5, etc. as primes, but we don't think as negative numbers as primes. Yeah, but here we are allowing negative numbers to be primes. Okay, so what does uniqueness mean? So uniqueness means that suppose there are two prime factorization, x equals p1 to pn, and it also equals q1 to qm, where p1 to pn and q1 to qm are irreducible. So we are not talking about prime but irreducibles. Yeah. Then n must be equal to m, and after some reordering, after a reordering, pi and qi's are associates. So what is an associate? For all I between 1 to n, that is pi is some unit times qi for some unit ui. Yeah. So let me just say more precisely that so maybe call this a definition. Let R be a ring, be a commutative ring with unity. Then let's take two elements and x, y be elements of R. Then x comma y are said to be associates. if there exists U in our unit such that x equals U times Y. Okay, so of course, if x equals a unit times y, then also y also equals a unit time x, right? Because you just multiply by U inverse. So it is indeed a symmetric definition. So associates is again a equivalence class. So if x, of course, is an associate of itself, and if x and y are associate, then y and x are associate, and of course if x is an associate of y, y is an associate of z. So it's denoted by it's denoted by x is, so this way, yeah, maybe, I mean, this is a makeshift notation, yeah, so don't take it too seriously. Any equivalence relation more or less we denote it this way, yeah. So note that this is an equivalence relation. So this is reflexive and symmetric is obvious. It's clear, yeah. And why is it reflexive? Why is it transitive? So suppose x is related to y and y is related to z, then what does this mean? So this implies that there exists uv in our units such that x equals u times y and y equals v times z, yeah. And then you can just write, so this implies, maybe I'll write it in the next line. So this implies x equals u, y, I'll replace it by vz, yeah, vz, but v times z, u times v, sorry, u times v is a unit. Is a unit. Product of two units a unit, yeah. Hence, x is equivalent to x is equivalent to z. Yeah, so this these being associates is a equivalence relation. So if you say that, so if you think of it as equivalence classes of irreducibles, then this is okay. So this then uniqueness, you can say it in the dot. Yeah. So in that sense, up to equivalence classes of irreducibles, it's unique. Okay, makes sense, everyone? So, so here also, I was going to say something about, yeah. So, in the definition of irreducible, you can say that x is irreducible if and only if and the equivalence class of its associates. Yeah. So the only so the equivalence classes of its factors are either the equivalence class of x itself or units. Yeah. So those are the only two equivalence classes. Then you can say x is irreducible. So then it is parallel to primes. Yeah. So the only factors are p and 1. So the equivalence class of 1 will be all of units, and the equivalence class of p will be itself. Yeah. In that respect. Okay, so that is so this is the definition of unique factorization domain, and as I argued, um, so integers z is a UFT. Yeah. So this we know from high school that every element we can write it as product of primes, and any two prime factorization will differ by will have the same length, and the only thing you can change is plus or minus. Yeah. So this is Z is a UFT. In fact, as I said, every PID is a UFT. Yeah. So Z is a PID, so it's going to be a UFT. So in fact, that is what we'll show. So in particular, after we prove this, we would have shown that um, not only integers but polynomial ring in one variable over a field is also a UFT. Yeah. Any questions so far?
Sir, could you please repeat that part about the equivalence class of irreducible?
Yeah, sure. So meaning the definition, how to interpret definition of irreducible in terms of equivalence class. Is that your question?
Yes, sir.
Okay. So, so when do we say that something is irreducible? If we can write, if we can't decompose it further as product of two non-zero non-unit. So that another way to rephrase it is that the only factors of x are the equivalence classes of factors of x are either units, equivalence class of unit, or equivalence class of x itself. So maybe I'll write it as well. So yeah, it's a good idea to write under this thing. Yeah, so maybe I'll write it here. So x is irreducible if, so maybe definition is something there, so maybe I'll put it if and only if y divides x implies equivalence class of so yeah, equivalence class of y is same as equivalence class of 1, or which is same as any unit. You can replace 1 by any unit, or equivalence class of y. So this is equivalence class in the with respect to associates. Yeah? Or another way to say it, so this is associate equivalence class. Or another way to say it is y is an associate of 1, or y is an associate of x. Yeah, these are the same thing. So that is what I'm trying to say. So the only factors of x are either an associate of 1 or an associate of x. Is that clear now?
Yes, sir.
Okay, good. Any other questions? Okay, unique factorization domain. Okay, so so the next thing we want to show is that every PID is a UFD. So in fact, we know that. So maybe I don't know if this was. So maybe it wasn't done in my high school, from what I remember. But it's been too long for my high school, so I may have forgotten parts of it. So I don't know if this is taught in school, that polynomials over say a field, over say rationals or complex numbers or real numbers, whether you can write it as product of irreducible polynomials or not. Probably not, because we don't talk about irreducible polynomials beyond degree 2. Yeah, something like that. We hardly talk about irreducible polynomial. Okay, so in particular, this will prove that polynomial ring in one variable over a field is a UFD. Yeah. So the proof is very intuitive in some sense. Yeah. So let's just try to. So we will try to first of all. So given a polynomial, how will you find a irreducible factor? You just try to do it in a. You try to find the smallest irreducible factor in some sense and so on. Or you can think of it in terms of integers. Yeah. So the way one would prove the integer case is more or less the same proof. Yeah. But you have to make the abstract versions of it. Okay. So so let yeah. So let X be an element of R, which is non-zero and non-unit. We want to show first of all that it has a prime factor, irreducible. We can factor it as product of irreducibles, and then we will show that it is unique, and we are assuming that our ring is PID. So prime factorization and irreducible factorization in this case is same, because in PID primes are irreducible. Okay. So first of all, since X is some non-zero non-unit, we can look at the ideal generated by X, and of course that is going to be a proper ideal. So we can find a maximal ideal P1 in R such that X belongs to P1. Yeah, is that clear? So we can always find a maximal ideal of R contain in maximal ideal in R such that X is in that maximal ideal, and we call that maximal ideal P1. So there may be many, we just pick one. But R is a PID, so this P1 is going to be generated by one element, which we call P1. Yeah. So there exists little p1 in capital P1 such that capital P1 is the ideal generated by little p1. And we know that X belongs to this ideal generated by little p1. So what does that mean? That means that X is a multiple of little p1. Huh? So that means there exists X2 in R such that X, which we can, so I want to label it in some reasonable way. So X1 is same as X, and we can write X, which is same as X1, as P1 times X2. Okay. So I'm trying to find out prime factors or irreducible factors of X. Yeah. So so I know that irreducibles are same as primes, and I know how to get prime numbers in PID. They are basically generators of the non-zero prime ideals. And how to get non-zero prime ideals? Well, non-zero prime ideals are maximal ideals in PID, and that is the route we are taking. Yeah. So we found non-zero prime ideal containing X, and that's how we got one prime factor of X, which is P1. Okay. Now, if X2 is a unit, then that's it. So our X is itself a irreducible guy. If X2 is a unit, that means P1 is irreducible. So if so another thing about associates is that so that tells you X is associate. If X2 is a unit, X is associate of P1. So if P1 is irreducible, of course X is irreducible. Yeah. So if X2 is a unit, then X equals X1 is irreducible, and we stop. So we have a prime factor irreducible factorization of X, which contains only one term. Yeah, so we can write X as product of irreducible. But if X2 is not a unit, then we repeat this step. Yeah. So again, we can find a maximal ideal containing X2 in R, which and from there we can get a irreducible a P2, which is going to be irreducible. So maybe I should write somewhere here that P1 is irreducible. Note, P1 is irreducible. Because P1 is prime and hence irreducible. Irreducible. Yeah, primes are always irreducible. So same is true about x1 if x2 is a unit. But otherwise, we repeat this step with x2. Yeah, so x2 is now a non-zero non-unit in R. So by the first step, we can find an irreducible element P2 and an element x3 in R such that x2 is P2 times x3. Yeah. So now we see what happens to our initial element, which is x1. Then x1 we can write it as p1 times x2, but x2 again is same as p2 times x3. Yeah. So x1 is p1, p2, x3. If x3 is a unit, then again we can stop. Yeah, and we can write x1 as p1 times x2. Where P1 we know is irreducible and X2 is some irreducible times a unit, and hence again X2 is irreducible. X2 is P2 times X3 is irreducible. Maybe I should change the color. If X3 is a unit. Okay. So if x3 is a unit, again we have found we are able to write x1, which is same as x, as product of irreducible. We can't do this, then we if x3 is not a unit, we continue this process. So we want to say that this has to stop, yeah. So we will prove that this stops via contradiction. So suppose this this process never stops. So if this never stops, what can we conclude? Then we will have a sequence of elements in R, x1, x2, x3, and so on. Yeah. So so suppose this never stops. So let x1, x2, x3, and so on be obtained by this process. So I won't be able to cut it out. So let me just write it more carefully. Be obtained by this process. Yeah. So we want to get some sort of contradiction. Yeah. So so we'll use the fact that our ring is a PID here again. Yeah. So consider the ideal generated by X. Actually, we'll use something much weaker. Okay. So I mean, such a process has to stop in most reasonable rings. But anyway, so suppose I is generated by x1, x2, x3, and so on. The ideal generated by all these elements which we have obtained. Yeah. Then I is an ideal of the ring R, and R is a PID. So what we get, that I has to be generated by one element. Yeah. So even if it was finitely many, that is good enough. But let's say, but we know here that I is in fact generated by one element. Yeah. Which is let's say Y. Since R is a PID, I will be generated by one element. And what do we know about these elements? So we know that x2 has to divide x1. Yeah. So this is how our construction was. x2 was a factor of x1. Yeah. So the ideal generated by x1 is actually contained in ideal generated by x2. So ideal generated. So since x2 divides x1, x1 is some multiple of x2. So x1 is contained in x2, and hence the whole ideal generated by x1 is contained in x2. Okay, and similarly x3 contains x2 and so on. So we have an increasing chain of ideals. Yeah. So such a increasing chain basically cannot exist. So it's in a PID or in a slightly more general ring. So why is that? So consider the idea. This ideal I, though we have taken it to be generated by x1, x2, x3, and so on, since this is an increasing chain of ideal, I is basically union of these xi's. Yeah? So of course, since it's an increasing chain of ideal, we know that the union itself is an ideal, and it contains x1, x2, x3. So of course, the right-hand side contains x1, x2, x3, and is an ideal. So it has to contain I, and of course I contains all of these. Yeah. So that tells you that this is an equality. So I is indeed equal to the union of these ideals, these principal ideals generated by xi. Now, of course, y, this element y, which is the generator of this ideal I, is an element of I, so it has to belong to one of these principal ideals. Let's say xn. Yeah. Then what we'll show is that this process has to stop. Then we'll get a contradiction to existence of xn plus 1. Yeah. So you can't possibly get xn plus 1 is what we'll show. Yeah. So suppose y belongs to xn, then y you can write it as some u times xn for some u in R, or some u in R. Yeah. Y belongs to xn precisely means this. Yeah. Also, xn is pn times xn plus 1. That is how our construction was. X2 is p2 times x3. So to construct xn plus 1, so if xn is not so xn is a non-zero non-unit, so you can write it as some irreducible times some other element of the ring. Yeah. So Pn is an irreducible, and xn plus 1 is some element of the ring R. Yeah. So that is how this is. So you can write xn as Pn times xn plus 1, where Pn is irreducible. And what do we know about xn plus 1? Xn plus 1 is also in I, yeah, because I is the union of all these guys, or I is generated by these guys. So xn plus 1 belongs to the ideal generated by I, which ideal generated by y, which is same as I. Yeah. So then xn plus 1 we can write it as multiple of y. Yeah. So xn plus 1 we can write it as v times y. But there lies the contradiction. So now we just make this chain complete. So y is u times xn, but xn is pn times xn plus 1. So what you get is y is u times pn times xn plus 1. And xn plus 1 is v times y. So you get u times v times pn times y. Yeah. So we get that y is u times v times pn times y. So now you can do the cancellation. So of y, so you get that u times v times pn is in fact 1, is equal to 1, not just a unit, but in fact 1. But pn is irreducible, right? So it's not a unit. So you can't have something times non-unit as 1. Yeah, a contradiction to pn is irreducible, and hence non-unit. So by definition of irreducible, it has to be non-unit. And if it is non-unit, no matter which element of the ring you multiply, you can't get a unit. Yeah, so maybe here I should write for some v in R. Yeah. Okay, any questions? So that tells us that this process of obtaining x1, x2, x3 has to stop at some finite place. Yeah. Hence there exists n such that xn is a unit. Yeah. So it has to stop, which implies x, which is equal to xn, is going to be p1 up to pn minus 1. Yeah, and xn will be, I think this numbering is okay. Yeah, pn minus 1 times xn plus 1. Yeah, so you can times xn. Yeah, so we can write, so if xn is a unit, then we can write x as product of p1 to pn minus 1 times xn, or maybe let's do it in 2 steps. Yeah, so x1 is p1 times x2, which is p1 times p2 times x3, and so on. This way you get that it's p1 times p2 times pn minus 1 times xn. Yeah, so of course where p1 to pn minus 1 are irreducible. So of course you have written it as product of irreducible. Xn is a unit, so you can absorb xn in any one of these PIs, but in particular you can just say, is you can write it as p1. So x we can write it as p1 pn minus 2 times pn minus 1 times xn. So this last term is also irreducible. Yeah, unit times a irreducible is again a irreducible. Okay, so this completes the proof that you can write every element as product of irreducibles. Okay, any questions so far? So this is how we will, I mean, this is how you will do it in practice as well. So if you have some element in a PID, then we try to find the first factor by, so for instance, think about polynomials. So we want, how do we factor it as product of irreducible? So their irreducibles are a little complicated, but we try to find out one irreducible factor first of all. Maybe there is a linear factor. So we try to figure out if we can find a linear factor or some irreducible factor. Then we divide by it, and whatever we get, we try to factorize, find another irreducible factor of that, and so on. So that is how you do. And eventually this has to stop because the degree will come into play. Okay.
Sir?
Yes?
So are all UFDs such that their ideas are finitely generated?
That is not true. So UFD could be, there are UFD in which ideals are not finitely generated. Okay. So UFD is slightly general, but anyway, the class of ideals which are class of rings where the ideas are finitely generated are an interesting class of rings, and we'll study them separately as well. Yeah. But it's not true that every UFD, in every UFD, all ideals are finitely.
Okay.
But in PID, of course, every ideal is generated by one element. Somehow I'm not able to move the screen here. Okay. Yeah, so the next part is uniqueness. So, so maybe we'll take a 5 minutes break and then do the uniqueness case. Okay. So let's take a break for, and we convene at 12. Yeah. Okay. Yeah. So so Shubhankar, you asked whether all integral domains with finitely generated ideals are so you asked both directions in some sense. So I already said that UFD need not have finitely generated ideals, and the converse is also not true. Yeah. So there are many rings in which all the ideals are finitely generated, but it's not UFD. So, for instance, we saw last time that Z adjoins square root of let's say square root of 5 is not a PID, so it's not actually not a UFD as well, and you can show that it is indeed finitely generated. Every ideal in that ring is in fact finitely generated. In fact, you can show that every ideal in that ring can be generated by at most 2 elements. Okay, so it's very close to principal idea. Any other questions? Okay. So let's come back to finishing the proof. So we have already shown that every non-zero non-unit in a UFD in a PID can be written as product of irreducible. Now we want to show that this can be done uniquely. Yeah. So let x suppose this element x, we can write it as product of p1 to pn and also q1 to qn be product of irreducibles. So I don't know how I've phrased it. Let x be such and be product of irreducibles. So i.e. P1 to Pn and Q1 to Qm are irreducible elements of R. Now P1 is irreducible and R is a so we are going to use the fact that R is a PID. Yeah? So P1 this P1 is irreducible. We want to show that n is same as m and P1 and Q1. So after some permutation of QIs, PIs and QIs are associates. Yeah. So what we'll do, we'll take one prime factor, one irreducible factor, and since R is a PID, it's a prime factor. So it divides the product of Q1 to Qn. Yeah. So P1 is a prime element, and since P1 divides X, which is product of Q1 to Qm, that means P1 divides one of these QIs. Yeah. So P1 divides QI1 for some I1 in 1 to m. Yeah, that is what we know because this is where we use the fact that P1 is a prime. Yeah? P1 is a prime element. Right? But QI1 is also irreducible. Yeah. So P1 divides QI1 means QI1 is U1 times P1, but QI1 is irreducible. So you can't have both U1. You can't have U1 to be non-unit. Yeah, because P1 we already know is not a unit. So U1 must be a unit. So this which implies P1 and QI1 are associates. Are associates. Okay, I should not yeah, are associates. Okay, but so what we will do is so as I said, we will reorder QI1. So Qs. So we can reorder Qs such that QI1 becomes Q1. Yeah. So what you do is interchange Q1 and QI1, for instance. Yeah. So after reordering, QIs, in fact, interchanging Q1 and QI1. We obtain that P1 and Q1 are associates. Right. Now we just write down the prime factorization again with some with this added information, and repeat the same. We'll repeat the same process with P2. Yeah. So what we have is X is maybe I should write it with black and mark these special things with red. Looks a bit ugly. So X, we can write it as P1 times Pn, and also Q1 times Qm, but Q1 is same as U1 times P1. Yeah, so Q, which is equal to Q1 times Qm, but Q1 is we have interchanged it with Qi1. Yeah, our associates, and we in fact have is that P1, sorry, Q1 is U1 times P1. Yeah, and U1 is a unit. So what we can write here is that U1 times P1 times Q2 up to Qm. Yeah. So we can so maybe I'll write P2 here and so on. So we can of course cancel these two. Yeah, to get P2 times Pn is equal to U1 Q2 up to Qm. Yeah. So again, U1 is a unit, so we can sort of forget about it. So what we get is that P2, this implies P2 divides, so U1, in fact, we can take it on this side as well. So P2 divides U1 inverse times P2 to Pn, which is same as Q2 to Qm, product of elements in R. And again, P2 is prime, implies it has to divide one of them. Yeah, so we are repeating the same process. I'm doing it twice so that it becomes clear for you. Yeah, so P2 divides Qi2 for some I2 between not 1, now we can even say it's between 2 to m. Yeah. So Qi2 is equal to U2 times P2 for some U2 in R, but Qi2 is irreducible, and P2 is also irreducible. That tells you that U2 must be a unit. Hence, U2 is a unit. So we get that Qi2 is an associate of P2. So again, we will reorder. Again, reorder Q's to get P2 is also an associate of Q2. So you just have to interchange Qi2 and Q2. Yeah. So in fact, I'll just write the formula because that is we also need this U2 somehow. Yeah. So I'm not going to repeat this further. Yeah. So P2 is associate of Q2. That's it. So we can continue this for all. We can keep continuing this till we reach Pn. Continuing this way. So my spelling of continuing is not right. Continuing, Tinuing. I hope this is okay. Continuing this way. We get reordering of Q such that Pi is an associate of Qi for I between 1 and n. Yeah. So this in particular also tells you that M has to be at least n, because I mean that's the only way this is, and as you can see, we can always keep doing this. Yeah. So and n and M is greater or equal n. Yeah. But by symmetry, so if we instead of starting by with P1 dividing Q1 to Qm, we can also say Q1 dividing P1 to Pn and try to find associates that way. We get that n has to be greater or equal m as well. So this must hence n equals m. And the statement about associates is already there. Yeah. So that completes the proof. Okay. Any questions? Okay. So if there are no questions, maybe since there was some question about examples, I'll talk about some examples, and then say more about the theory. Yeah. So rather non-examples. Okay. So let's see. I can't minimize this. Okay. So where do I put it? 1 second. I do want to keep this thing, so I'll do this impromptu. Sorry about that. So yeah, so we'll put it here. Yeah, this is not a good idea. Okay, yeah, it's come out okay. So let's just okay. Okay, I'll write it here. So you can see, right? Yeah, so the uniqueness parts proof is here. Okay, and so let's see some examples. Okay, so maybe some examples of rings which are not UFD. So first of all, or maybe first examples of rings which are UFD. So of course, every PID is a UFD. So Kx, where K is a field. Fields are also UFD by so sort of vacuously, because there are no non-zero non-unit. And but something which we will see later, that this ring Zx, which we decided is not a PID, is actually a UFD. Zx is a UFD. Yeah, so this we will, so we haven't seen this, but we'll see this later. In fact, what we'll see is that polynomial ring in any number of variable over a field or integers is a UFD for k field or k equals z. Even for k equals integers, this is okay. So in fact, what we'll show is that if R is a UFD, then Rx is a UFD. Polynomial ring over it, that is a UFD. I think that's yeah, that's something which we will see as well. I hope. Then yeah, so now, so as you can see, you can cook up UFD. So though PIDs, if you take polynomial ring over a PID, you don't remain a PID unless you start. But in that respect, UFD is better. You can manufacture more and more UFD from a given UFD by just adjoining more making bigger polynomial rings. But there are many rings which are not a UFD. So for instance, of course, so even if it's an integral domain, it may not be a UFD. So, so first thing is to show that this ring, so non-examples maybe. Okay, so non-examples. So maybe I'll tell you more details. Yeah, maybe this one, z square root 5. This was the ring we were discussing, right? Yeah, I think this, or I think I was discussing z square root minus 3. One of these two. I don't remember which one I was discussing. Probably this one is not UFD. So it's in fact not a PID is what we showed. So they are actually neither PID nor UFD. Yeah. So one would want to show that. So how would one show that it's not a UFD? So one way to show is that this definition fails. So you have to find an element which doesn't have a unique irreducible factorization. Yeah. Or one can show something like or one can find some property of UFD and show that that is not true for these rings. So there is one property which I want to discuss next, and that will help us decide this. So this, I haven't given you a proof, but I'll just tell you this is one example. What you can also do is consider Q X, Y, and you know, you go mod something. So yeah, but I'll try to do something more natural. Yeah. No, so maybe 2 is enough. Yeah. So let's just 3 maybe is enough. X, Y, Z. Yeah. So go mod X minus Y, YZ. The ideal generated by X minus YZ. So this is no, this is actually a UFD. Sorry. So let's just do W as well here. Yeah. So I'll show that this is a UFD as well, but let's just XY minus CW. So this is not a UFD. Yeah. So what happens is basically there is one element. I mean, if you look at this quotient, so I'll give you an intuitive idea about this thing, and we'll do this more rigorously later. So what are the elements of this ring? It's equivalence classes of polynomials in 4 variables modulo this ideal. Yeah. So by bars we will denote the so it contains x bar, y bar, z bar, w bar are elements of this ring. Yeah, where x bar means the quotient represented by x. Yeah. So so this ring also contains x bar times y bar. Yeah. x bar y, let's call this ring R. Yeah, so x bar times y bar belongs to R. Yeah, and what you can show is that x bar and y bar are in this individual element, x bar and y bar and z bar and w bar are indeed irreducible. Yeah, so they are irreducible. So you can't, that is, you can't decompose it further. Um, so this element x bar y bar has a decomposition. Yeah, so it is say you have written it as product of irreducibles x bar times y bar. Yeah, but x bar times y bar is the same as z bar times w bar in this ring in R. Why? Because x bar x minus xy minus zw is 0. Yeah, so x bar times y bar is same as z bar times w bar, and this is another factorization of x times y into irreducible factors, and they are not the same. So x and x bar and z bar are not associates, and y bar and w bar are not associates. But x bar as x bar y bar z bar w bar are irreducible, but none of them are associates to each other. Okay, so this is what happens with these guys. Okay, so I was gonna do one more property of UFD. Okay, so yeah, let's see. Maybe this is not too long. So this is something which we saw for PID. That in PID we saw that irreducibles and primes are same. Yeah, so the same is true for UFD. So let R be a UFD, then and X belongs to R, and X be an element of R. Then X is irreducible if and only if X is prime. So of course, the reverse direction is true for integral domain. So X is prime implies X is irreducible is true for any integral domain, and hence for UFD. So the only thing one has to check is the forward direction. So this is not long. So maybe we have about 5 minutes. So I think this, we can do this in the 5 minutes. Yeah. So this is just one or two lines. So enough to show this direction. Yeah. So we are assuming X is irreducible. We want to show that X is a prime. So to say X is a prime, we have to show that if X divides AB, then X has to divide A or B. Yeah. So suppose X divides AB for AB in R. Yeah. Then this implies that we can write AB equals X times Y for some Y in R. Yeah, that is what X divides AB means. Right. Now we write so X is, remember X is an irreducible. Yeah. So now what we do is we write A is some element of R. Yeah. So if A is a unit, so if A is a unit or B is a unit, then X divides B or X divides A. Yeah, and we are done. So we can assume that both A and B are non-units. Yeah. So if one of them is a unit, then there's nothing much to do. Yeah. Otherwise, well, A and B are non-units and they are of course non-zero. So we can, and R is a UFD, so we can find a prime factorization of A and B. Yeah. Otherwise, there exist P1 to Pn in R irreducibles and Q1 to Qn in R irreducibles, such that A we can write it as product of P1 to Pn, and B we can write it as products of Q1 to Qn. Okay, so what do we get? We get that X times and Y also we can write it as product of irreducibles. So maybe also Y is C1 to maybe say PQR R1 R1 to RK Ri is irreducible in R. So what we get is X times R1 times RK is equal to P1 to Pn Q1 to Qn. Yeah, from this identity. So let's label this star from star. Yeah. Now uniqueness of irreducible factor irreducible factors. So these are all irreducible. X was irreducible. R1 to RK are irreducible. These are all irreducible. Yeah. So for the same element, we have two irreducible factorization. Uniqueness of irreducible factorization tells us that X has to be associate of one of these guys. Implies X is an associate of Pi for some I, or either it could be associate of Qi's as well. So, or X is an associate of Qj for some j between 1 and n. Yeah. So the first statement will imply that X divides product of Pi's, which is A, and the second will tell you that X divides product of Q, which is P. Yeah. So we started with X dividing so we started with maybe X dividing A times B, and we concluded that X has to divide either A or B. Okay. So that completes the proof. So we saw that even in UFD, every irreducible is indeed prime. So next time we will also show that this fails. Yeah. So in particular, we will show that this fails in this ring, these rings, even here. Yeah. So far you haven't seen an example of a irreducible which is not prime. So here, for instance, we will show that X bar is irreducible but not prime. Or here we will show something. So I think maybe 1 plus square root of minus 3 is probably going to be irreducible, but it's not going to be prime. Okay. So we'll show these things, and that will conclude that these guys are not a UFD. Okay. Any questions? Okay, so this is the last thing I want to do. So there are some questions in the chat. I'll answer that, and we'll call it a day. Yeah, so Shoham, the coefficient Q is not important. You can take any field there. Yeah. Okay, so that's what Anupam said. Yeah, so you can take any field and it's okay. Any other questions?
Sir, why do we need a field?
Yeah, so maybe you don't even need a field to say so, but the point is if you take some crazy ring, then of course for some other reasons it may not be a UFD. Yeah. So I want to take the nicest possible ring and say that if I take some other field or something, nicest possible field, even C is the nicest possible field. It's an algebraically closed field and so on. Then also it is not a UFD. Yeah. So of course, if you take a crazy ring, then it's not. So Z is more complicated than Q, then that will also work and so on. Yeah. So all this will work. Some crazy rings will also work, but let's take something nice and still so it's not a UFD. So it's a very reasonable ring in many aspects, but still not a UFD. Any other question? Okay, so if there are no questions, we'll meet on Thursday, and I'll put up homeworks for which will be due next Tuesday. Yeah, and next Friday we'll have not this Friday, but next Friday we'll do another quiz covering maybe Euclidean domain, PIDs, and UFDs, and so on. Okay. Okay. Bye bye.